Hello, and welcome to Cruising Through Calculus. My name is Alex, and today we're going to be going over optimization problems. So, let's jump right in. Our first problem says, a rancher wants to construct two identical rectangular corrals using 500 meters of fencing. The rancher decides to build them adjacent to each other, so they share fencing on one side. What dimensions should the rancher use to construct each corral so that together they will enclose the largest area possible? So whenever you're doing optimization problems, the very first thing you want to do is you want to sketch a picture and then label it. So let's do that. Here we have two corrals, which are supposed to be identical, like this. And we know that there is 500 meters of fencing, so that's kind of like the perimeter of this. So let me write that down over here. 500 meters is the perimeter. And let's go ahead and let's label this. Let's say each of these is y, and then let's take this entire distance down here and let's call that x. All right, so I've drawn a picture here, I've labeled it. Let's write down what they want us to find. They want us to optimize the maximum area. Now, this is important because this is going to tell us what our primary equation is. Anytime you're doing optimization problems, you always have to start by finding a primary equation. Now, since we're optimizing area has to be the primary equation that we're working with here. And we're trying to find the thing that maximizes the area of this shape here. So I hope you can see that the area of this entire shape here is just going to be x times y. Now that we've found our primary equation, it's time to find our secondary equation. Our secondary equation has to do with the information that they gave us in the problem. In fact, I wrote it down right here. This is it. They gave us that the rancher has 500 meters of fencing to use. So if you look here, that means he'll have 500 meters to enclose this, 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 and this. Or in other words, the perimeter, which is 500, is going to be equal to x plus y plus y plus y. Now, the reason why we need a secondary equation is because what we want to do is we want to get our primary equation to have a single independent variable. Right now we have x and y. I would like for this to be only x or only y. That way I can just find the derivative like I normally would. We can do that with our secondary equation here. In fact, if we take our secondary equation and we solve for x, let's do that really quickly. 500 minus 3y equals 2x. Divide each side by 2. 250 minus 3 halves y equals x. I can now take this and substitute it in up here for x. So area is now 250 minus 3 over 2y times y. And now I have everything in terms of y, just a single independent variable. Let's go ahead and let's distribute this y out. We're going to get 250y minus 3 halves y squared. This is perfect. Now that we've drawn up our picture, labeled it, wrote out what they gave us, what they want us to find, found our primary equation and our secondary equation, and we substituted our secondary equation in and simplified it here, we can use either the first or second derivative test to find either the minimum or maximum. Now here we are trying to maximize the area, so that should be what we get. Let's go ahead and let's start by finding the derivative. Okay, so we're going to get 250 minus 3y. Now what we're going to do is we're going to set this equal to 0. So if I do set this equal to 0 and I add the 3y over here, I'm going to get that 3y is equal to 250, or y is equal to 250 over 3. Now, here's a question. This value that we found, is this a local maximum or a local minimum? Well, hopefully it is a maximum, but you really want to check just to make sure. Now, you could use the first derivative test, like I said, or the second derivative test. I'm going to use the second derivative test. You should use the second derivative test too if finding the second derivative is easy. And check this out. The second derivative is super easy here. We're just going to get -3, which kind of answers the question for me. Normally what I would do is I would take this and plug it into my second derivative, but notice that there's no y's over here. That just means that we always have a negative answer for our second derivative. And according to the second derivative test, if you get a negative result, that means you're going to have a local maximum, which is perfect. That's exactly what we want here. So I know based off of the second derivative test that this is going to be a local maximum. Now, this gives me the y coordinate here, but what about the x coordinate? Well, if you look right here, I actually have a way of figuring out what x is equal to. It's 250 minus 3 halves y. So all I need to do is take 250 thirds and plug it in here. Now, check this out. The 3 will cancel with the 3. 2 does fit into 250 125 times, and then 250 minus 125 is 125 right here. So now we know what this length has to be. Now, depending on how the question is set up, there are numerous ways that you could actually label things. For example, I decided to call this entire length here x, but just for a moment, pretend with me that we had decided to label just this part here x, which would also make this part x as well. If we were to figure out the answer to just this part of his corral, we'd have to take the entire distance that we found and divide it by 2. So each of these smaller individual pieces would be 125 over 2. Like I said, depending on how the question is set up or perhaps how it's phrased, you might need to find the smaller value instead of the larger value. Our next problem says, a supermarket employee wants to construct an open top box from a 10 by 16 centimeter piece of cardboard. To do this, the employee plans to cut out squares of equal size from the 4 corners so the 4 sides can be bent upwards. What size should the squares be in order to create a box with the largest possible volume? All right, this is a classic question that comes up all the time in optimization problems. So let's first start by drawing a picture. So let's say that we have a piece of cardboard here, and we know that one side of the cardboard is 16 centimeters long, and another part of the cardboard is 10 centimeters long. Now, what the employee is going to do is take this flat piece of cardboard and then cut out identical squares in the 4 corners. Now, we don't know how big he's going to cut these out yet, so let's call that distance there that he's going to cut out x. And since these are identical and they're squares, all of these here are x's. So x, 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 and x, although I won't write all of them down because that seems a little unnecessary. Now, this is the interesting part here, because if you imagine actually cutting these out here, you would actually be able to fold up the sides and then create a box. Now, this is an open top box here, meaning that there's nothing up here, but there is a bottom of the box. So, okay, I've drawn a picture here. There are a couple more things that I do want to label, but I'm actually going to wait on that for just a second here, because I want to talk about the primary equation. The primary equation is going to be whatever we're optimizing, and we're trying to figure out what the largest volume is that this box, or that we can cut out of the sides here to get a box that gives us the most volume. So I need an equation for volume. Now, if you have a shape like this and you want to find the volume, you just need the length times the width times the height. So what we need to do is figure out what the length and the width of the height is of this box over here, given this here. And we can do that. For example, check this out here. If this side here is 10, and if I cut out some amount here and then the same amount here, which we're calling x, that means that the leftover part has to be 10 minus 2x. Similarly, we're going to take the 16 starting point here. We're going to cut out the x here and the x here. So this is going to be 16 minus 2x here. And then, of course, we are cutting out x right here. So x is the amount that, when we fold this box up, will be the height of the box. In other words, what we've found here is we found everything that we need for the actual folded box. The height of the box is x, and then the lengths and widths are the 10 minus 2x and the 16 minus 2x. So now I know what volume is. Volume is going to be x times 10 minus 2x times 16 minus 2x. Right? The height is x, and then the length and width is the 16 minus 2x and the 10 minus 2x. This is perfect, because now we have an equation where there's already just a single independent variable, which is x. So I actually don't even need to find a secondary equation, which most of the time you do in these problems. All right, so here's what we're going to do. We're going to multiply this entire thing out here. Now, I've already done this ahead of time here, and what you end up with is this. You get 4x cubed minus 52 x squared plus 160x. So you're going to have to multiply this x out, distribute it, and then FOIL whatever's left over, and then combine your like terms to get this. Once you have this, you can find the derivative, and you can set that equal to 0. So let's go ahead and find our derivative here. This isn't going to be too bad. This is going to be 12x squared minus 104x plus 160, and we're going to set that equal to 0. Now, when we do this, there's something I notice immediately, which is that all of these are actually divisible by 4 here. So let's go ahead and divide both sides by 4. That'll actually give me a 3 here. Let's see here. That is 26, and this one is 40. All right, so now what we need to do is solve this. Now you can use the quadratic formula, but this is actually factorable, if you can believe it here. So if we do 3 times 40, that gives us 120. Now, what multiplies to 120 and adds to negative 26 is negative 20 and negative 6. So I'm going to take this and break it up. We're going to do 3x squared minus 6x minus 20x plus 40. Then I'm going to factor what I can from the first half of this, and then I'm also going to factor what I can from the next half of this. When I do that, I get a common factor here and here. Both of these are x minus 2, which is perfect. That means I can take the x minus 2, factor it out, and what I'm left with after factoring the x minus 2 is the 3x minus 2. Now, I have two answers here. If you solve each of those, we get x equals 2, and we get x equals 2/3. Okay. So the real question then is, which of these is the correct answer? And actually, I just realized I made a tiny mistake here. When I was factoring here, I factored a 2 out. I meant to factor a 20 out, which luckily doesn't change very much. That just changes this to a 20, and that means that this is 20/3, not 2/3. Okay, good. I'm glad I caught that. Now, what I was about to say before I noticed that is, well, we have two answers here. Which of them is correct? Is one of them the local maximum and the other the local minimum? Well, we got to figure that out. So what we're going to do is we're going to take our first derivative, and we're actually going to find the derivative of that. I'm going to use the second derivative test, in other words. Always use the second derivative test if it's easy to find the second derivative, and it is definitely easy to find the second derivative here. Check it out. It's going to be 24x minus 104. We're already done. All right, now that we have our second derivative, all we need to do is take our values and plug them in. So let's take 2 and plug it in for x here. Then let's take 20/3 and plug it in. What we're looking for are positive or negative numbers. So for example, 2 times 24 is going to be 48, minus 104 is definitely a negative answer for sure. Then let's see what happens when we plug 20/3 in. So 20/3 times 24. Well, that's not super nice, but let's see if we can do it. Because 3 does fit into 24 8 times. 8 times 20 is going to be 160. So we're going to get a positive answer here. This is good because this tells me what the answer is. If the second derivative has a negative answer, where the first derivative is equal to 0 and you plugged it in, that must mean that this right here is the local maximum. So I now know what the answer is. The answer to this question is x equals 2. So in other words, if this employee does want to create a box that holds the most volume, and he's starting with a flat piece of cardboard, all he would have to do is cut off 2 centimeters from each side and then fold it up, and that'll give him the most volume. Our next problem says, which point or points on the graph of y equals 5 minus x squared are closest to the point 0, 2? All right, so let's start by drawing a picture here. Y equals 5 minus x squared is an upside down parabola because of the negative x squared that has been shifted up 5 times. Now, we want to know if we have the point 0, 2, so let me label this right here. This is our point, 0, 2. Which of the points on our parabola is closest to this point here? So I think you can see that if I drew a line, say, from here down to here, that would be longer than from here to here. And then maybe this would be longer too. It seems like maybe our answer is somewhere over here. But what is it exactly? Well, that's what makes this problem challenging. So let's start with this. Let's go ahead and just pick a random point that is on our parabola here. And we don't know what this point is yet. I'm putting it maybe approximately where I think it might be. And let's call that xy. So what we want to do is we want to minimize the distance between our point 0, 2, and then our other point, which we don't know yet, x, y. So you have to think to yourself, we're trying to optimize this problem by minimizing the distance between 2 points on a graph. What sort of primary equation uses that? Well, it may have been a while since you've used this, but this is going to be the distance formula. You can actually use the distance formula when you're finding the distance between 2 points on a graph like this. And that's exactly what we're going to use here. Let's see here, this should be y2 minus y1 over here. So this is our primary equation. And normally I would just jump straight into finding the secondary equation, but just before we do that, let's go ahead and let's take 0, 2, and then x and y, and let me take these and plug it in up here. So let's say that this is x1, y1. Let's call this x2, y2, and let's start plugging it in. So let's see here, x2, it's going to be x minus 0 squared, which is just going to be x squared, plus y minus 2 squared. Of course, the whole thing is square rooted. All right, like I said, this is just going to turn into x squared, which is nice, but we do have two different variables here. So we do need to use our secondary equation here, and they actually gave us the secondary equation. It's the parabola. The point has to touch the parabola, and the parabola is given by y equals 5 minus x squared. So what we're going to do is we're going to take this and plug it in for y right here. So let's see what we get here. I know we're going to get x squared over here. Then over here, what we're going to get is, it's going to be 5 minus x squared, and then minus 2 squared, and then all square rooted. Now, 5 minus 2 is 3, and then you're going to have 3 minus x squared, quantity squared. And what I recommend at this point is to actually go ahead and expand the whole thing and collect all like terms. Now, I've already done that, and when you do that, you get this. X to the fourth minus 5x squared plus 9, square rooted. Perfect. We now have a primary equation, distance, which only has x in it, so a single variable. That means we can find the derivative, set it equal to 0, and use either the first or the second derivative test to see if we have a local minimum or maximum. Now what we could do, and this would work, we could take this whole thing, raise it to the 1/2 power, and then use the chain rule, and that would be fine, but there's actually a faster way to do this. And I bring this up because when you do optimization problems, distances actually come up fairly frequently, so this is a tip to keep in mind. When you're trying to minimize distance, you can minimize the inside of the square root, because when you minimize the inside of the square root and then you take the square root of that, you should get the same answer, if that makes sense. So let's just find the derivative of the inside, in other words. Okay, we're going to get 4x cubed minus 10x. Now let's set this equal to 0. We're going to factor a 2 and an x out. Then we're going to set each of these factors equal to 0. We're going to get 0 over here. Over here, we're going to have to add 5, divide by 2, and then take the square root. When you take the square root of both sides of an equation, don't forget to include the plus or minus here. So you can see that we actually have 1, 2, 3 answers here. So which one is actually the point that will be the closest to 0, 2? Well, there's a couple ways we could do this. One thing you could do is you could just take these numbers, plug it back into our distance equation here, and see which one gives you the least distance. That would work. I'm going to use the second derivative test again, though. This is what I recommend you use if it's easy to find the second derivative, which it is here. Check it out. Second derivative is 12x squared minus 10. And then I can even factor a 2 out. I don't know if I really need to, but I guess I will. 6x squared minus 5. Now, all we have to do is just take our numbers and plug it in here and see if we get positive or negative answers. And actually, now that I'm looking at this, I think I'm just going to leave it as the 12x squared minus 10. Sometimes factoring helps with these, other times it doesn't. All right, let's start by plugging 0 in. That's really easy. We're just going to get negative 10 here. Okay, let's go ahead and plug either positive or negative square root of 5 over 2. Now normally I would do this twice, or maybe once each for the positive and once for the negative version. But check this out. Whether I take the positive or negative version, I'm plugging it into this x squared piece here. When I square it, whether it's positive or negative, I'm going to get the same thing. So I can actually save myself a little bit of work here by just including the positive and negative version at the same time. Like this. Okay. Ooh, squared minus 10. There we go, that's better. All right, let's see what we get here. This is going to be 12, and then times 5 halves, and then minus 10. Well, okay, let's see here. This and this will give me 6. 6 times 5 is 30. 30 minus 10 is a positive number. Okay, perfect. So now we have our answer here. We know that when we get a negative result, we get an absolute maximum. When we get a positive result here, that means we have an absolute minimum, and we're trying to find the point that is closest, so we're looking for the minimum. That means this is what we're looking for here. So I now know that either positive or negative root 5 over 2 for x will give us the closest point to this. But notice it does want a point, and this is just an x-coordinate. I would need to find the y-coordinate as well. That means I'm going to have to take this and plug it back up into my original equation to find the y-coordinate. So let's do that. Y equals 5 minus. Now, this is interesting because just like before, whether I take the positive or negative version, when I square it, I'm going to get a positive answer here. So what we're going to get is 5 minus, and this will be 5 over 2. The reason why I'm leaving this blank is because I am now going to get a common denominator. So I can easily subtract the 2, and there we go, we get 5 halves. So we now have our answer. The point, or actually the points, which are closest to 0, 2 that are on our parabola are either, let's see here, positive or negative root 5 over 2, and then the y-coordinate is the same, 5 halves, which makes sense. There's some symmetry here. The y-coordinate should be the same while the x-coordinate is the one that's changing. And thus, that is our final answer. Our next problem says, a manufacturer needs to make a cylindrical can that will hold 1.5 liters of liquid. Determine the dimensions of the can that will minimize the amount of material used in its construction in centimeters. All right, let's start by drawing a picture. Let's draw a can here. Now, every can will have a certain height and a certain radius. And believe it or not, I think that's all we have to label just for the moment. All right, now the next thing is that they told us there is 1.5 liters of volume here. Now this is one of those problems where you have to be careful with the units, because they gave us 1.5 liters, and yet if you look at the question, it specifically says they want the answer in centimeters. And the good news is converting liters to centimeters is actually easy. We just have to move the decimal place over 3 times. So our volume in centimeters is going to be 1,500. That's the number we're going to be using as we go through this. All right, with that part out of the way, let's see if we can find a primary equation that fits this. They want to know what will minimize the amount of material used. And if you think about it, that's really the surface area of our can. So what we need is an equation for the surface area of a can. So we're going to need the top circle and the bottom circle, which is going to be pi r squared, but there are 2 of them. And then we're going to need the area of the middle section here, which is really just the perimeter of the circle, or the circumference, times the height. So that's going to be 2 pi r, that'll give us the circumference, and then of course the height here. This is the equation that we're going to be finding the derivative of. But wait a second. Notice that there are 2 different variables here, r and h. That means we're going to need a secondary equation. And that's where our volume is going to come in. So we know that the volume is already 1,500. Well, what is the volume of any can? Well, that will be the area of the circle times the height. So that's going to be pi r squared times h. This is perfect because now we can take this equation and figure out what h is equal to. H is equal to 1,500 over pi r squared. And now we can take this and substitute it in here. Let's see if anything simplifies when we do that. And in fact, things will simplify. Check this out here. This pi will be gone, this pi will be gone. One of the r's here and one of the r's here will be gone. So we'll be left with 2 pi r squared. That part didn't change. Then we've got 2 times 1500, which is 3000. And then we have an r in the denominator. I'm actually going to bring that up to the numerator like this, because we're about to find the derivative. So let's find the derivative here. We're going to get 4 pi r minus 3000 r to the negative 2. Now let's set this equal to 0 and see if we can figure out what r is equal to. Now, I can already tell that when we're doing this here, we're going to need to get a common denominator, because I'm going to take this r to the negative 2, move it to the denominator here, which means I'm going to have to multiply this side by r squared. So if I do multiply this side by r squared over r squared, I'm going to get 4 pi r cubed minus 3000 all over r squared. Now, when you have something like this set equal to 0, you don't need to worry about the denominator. You only need to worry about the numerator. So what we're going to do is we're going to take the numerator and set it equal to 0 here. Now, I am kind of skipping a step here. If we set the numerator equal to 0, I'm going to add the 3000 to the other side. Then I'm going to divide by 4 pi. And then I have to take the cubed root of both sides to figure out what r is. Now, let's see here. I plugged this into a calculator, and I got 6.2, approximately. And this is in centimeters. So now the question is this a local minimum or a maximum? Well, here, let's come back to our first derivative before I move this into the denominator, and let's go ahead and find the derivative again. We'll plug this number in, and we'll see if we get a positive or negative answer. Okay, so we're going to get 4 pi, and it's going to be plus 6,000, and then I'm going to kind of do this over r cubed, because we're going to get r to the negative 3, and I'm going to move that to the denominator. And check this out. This is actually kind of interesting. R is 6.2. That's a positive number. Over here, notice r cubed. So if we take 6.2 and cube it, that's going to be positive. Positive divided by positive is still positive. 4 pi is positive, plus another positive is still positive. I guess what I'm saying is that if you substitute 6.2 in for our surface area here, you're going to get a positive answer, which is perfect because they wanted us to minimize the amount of material used on this can here, and that's what the second derivative test says. It says if you get a positive answer for your second derivative, when you take your first derivative that's set equal to 0 and plug it in, and you get a positive number, that means you get a local minimum. I know I kind of repeated myself there. Okay, this is great. I now know that the radius of the can should be 6.2. All I have to do now is find the height of the can. And luckily for us, I have an equation right over here that will give me the height of the can if I know the radius, and I do now. So the height of the can is 1500 over pi times r squared. Now, just for the moment, I'm going to do 6.2 squared, but actually I already did this beforehand, and when I plugged this into my calculator, I actually took this exact piece and plugged it in here. So if you plug 6.2 in, you might get a slightly different number than me, but it'll be really close. 12.407 is what I got here. So there we have it. We now know what the dimensions of the can would be that would minimize the amount of material used for our can. To help you out, here were the guidelines that I was using when I was solving these problems. The first thing you always want to do is to draw and label what's going on with the problem they gave you. You might even want to write out specifically what information they give you and then what they want you to find. Then the next thing you want to do is to find a primary equation. Now, this is always tied to whatever's being optimized. So if it's a volume that's being optimized here, you need to find an equation for volume that matches your picture. Now, usually, not always though, you need to find a secondary equation, which is based on the information that they gave you at the beginning. Once you find that, you're going to plug it into your primary equation and simplify it down to a single variable. Now, every once in a while, your primary equation will already have a single variable and you won't have to worry about this. This actually happened on our box question that we went over. In either case, once you do get it to a single variable, you want to use either the first or the second derivative test. What that really means is taking the first derivative and setting it equal to 0 and see what you get. You do need to make sure that what you get is either a local minimum or maximum though, because sometimes you'll get problems where there are multiple answers and you're not sure which one it is until you use one of these tests. If you found this video helpful, you might consider checking out my website, which is linked in the description below. You'll be brought to Infinity Learning Academy, where you can find Cruising Through Calculus. At Cruising Through Calculus, we have over 100 videos and documents to help you get through your calculus class, including videos for each topic, practice problems, and full video solutions for those practice problems. I hope to see you there, and together we can cruise through calculus.